I plan to quickly talk a little bit about who LHP is, and then we'll get right into this case study for rapid control prototyping for a variable valve timing solution. And then I'll go through some challenges we ran into and how we overcame those, and then some next steps on the system. A little brief introduction on LHP Engineering Solutions. We are headquartered in Columbus, Indiana. We do have offices here in Pontiac. We're primarily known for our expertise in engine controls, model-based design. We have on-site engineering resources, and we do project-based work, and we also build some products, which you'll see one of those here today. We are a National Instruments Alliance partner. We're also a MathWorks product partner. And this SAE logo is because we do SAE certified training also. And the Panthera tool, which you're going to see today, is available on the National Instruments LabVIEW Tools Network as well. This is just a little bit about some of the tools that we provide that support the development cycle all the way through the development V. We kind of have this integrated workflow. So early in development, we have our prototyping tools. As you get into implementation, we have tools to help support that, and we do hill tests for V&V. So we have tools throughout the product life cycle. So I'm going to get right into variable valve timing. Some of you already probably know some of the benefits of variable valve timing, so I'm not going to get too much into that. But one thing you'll notice in this chart on fuel economy improvement technologies is that a couple of the key technologies being used are cam phasing and variable valve lift. So they're really critical to fuel efficiency. They also affect and can be used to improve the engine output, fuel consumption, and your exhaust, your emissions. So basically, variable valve timing is used in internal combustion engines to control the breathing across the operating speed and torque range. So researchers need to be able to independently control the valve opening and closing profiles on the exhaust and the intake valves in order to optimize and tune the engine. So during research and development, you can actually test using a variable valve timing system like this, test different valve profiles to find the optimal solution that then can be used in your production environment. So as an example, you might have a cam switching system that only has 2 cam profiles that you can choose from on your production system. But in R&D, you can try different cam profiles and find the best 2 cam profiles, depending on speed or torque or your performance profile. And so that's basically what this system was used for, is to test over a wide range of conditions under a wide range of valve profiles to find the optimal solution. This is not the actual application, but it is representative of a variable valve timing system similar to what was used. So in this particular case, the client already had these electrically controlled valves. They had a control system that was capable of 1 crank degree resolution, but they needed better. They needed a 0.1 crank degree resolution on the valve position control. They did want to use Simulink models to control the valve positions, and they also wanted to use National Instruments hardware. And this is where our Panthera suite comes in, because the LHP Panthera RCP suite allows you to have the Simulink experience on National Instruments hardware. So this is just kind of a slide showing that because we are a MathWorks partner, we're also a National Instruments partner, we're kind of uniquely positioned to bring those 2 technologies together. So this is a high-level overview of what is in the system. And actually, if I can figure out this pointer, on the upper right is showing the Simulink control model using our Panthera block set. So you develop your control strategy in Simulink to be deployed on, in the center here, this big box represents your control system. In this case, we're running on Linux real-time. It's Simulink enabled by our Panthera suite. There is a dual-core microcontroller and FPGA in the system, and then it connects through the hardware. These are the C-series slots on your C-Rio chassis. So that connects to the valves to send the command, the valve actuation command, and it also reads the valve position feedback. And of course, it's also connected through sensors to the cam and crank position, so it knows engine position. There's CAN communications and things like that. Now, also depicted up here on the upper left is your measurement and calibration. So in real time, as the system's running, you can measure and calibrate using any of your industry standard tools like ATI Vision or ETOS Inca, because we generate the A2L files when we do the build of this control model. So with the cards that were already selected for us, we had a few issues. We had to analyze whether they were capable of doing the job. And we were given a maximum engine speed of 1800 RPM, and of course the target of running a 0.1 degree, I went way too far, a 0.1 degree crank resolution. So the question, of course, was, are these NI cards really capable of meeting these requirements? So we did some analysis on that. If we look first at the engine position card, so this was the NI 9375, it can acquire a sample every 7 microseconds. So at the 0.1 degree, you can get up to 2381 RPM, which of course is more than 1800, so it does meet the target. There are some other cards that we would recommend for a better resolution. These cards are really intended for VR or Hall type cam and crank signal inputs, and they can run to 25 nanosecond speeds, so obviously it's much faster. Gives you higher resolution on your engine position. The valve position feedback card, so this is our analog input for the position sensor, is the 9201. One thing you see is it's 12-bit, whereas our output is 16-bit, so we have a little bit of a resolution mismatch. And it acquires on the 4 channels at 8 microseconds. So again, we calculate up that we can achieve our 1800 RPM target, but barely. One problem with this is, since this is in our feedback loop for valve position error correction, we're not accounting for Nyquist, or we don't have any oversampling and filtering on that feedback. So any noise that gets in there can really kind of wreak havoc with our control error correction. And then our valve position actuator is the 9263, which is, again, it's good enough for the up to 2200 RPM for the 0.1 degree accuracy target. But we did recommend some higher speed cards for the next generation system, which I'll talk about a little later. So the hardware we were given is capable. We had to do some tricks in the FPGA. So this is a quick shot of one part of the FPGA that's controlling this. If you look on the far right, that's the analog output command to the valves. So we've got the exhaust valve and then the intake valve both being commanded out in this 8 microsecond control loop. And if you look here, we're actually measuring the feedback of the valve position, and then we're doing our error correction based on the previous sample, and we scale that from millimeters to volts before we send it out on the analog output. So this whole control loop for both exhaust and intake valves is running in an 8 microsecond control loop on the FPGA. So then the next challenge is, how do we transfer the profiles down to the hardware? So these valve profiles are being determined in Simulink and then sent down to the hardware to run the actual exhaust and intake valves. So of course you have to synchronize it with engine position. You can't just change it while it's generating a valve profile. So we had to look at how much time do we have to make the transfer. So what we did was split it up into transfers of the open profile and then the closed profile for both the exhaust and the intake valves. So there are 4 total arrays that need to be transferred. There are 200 elements each at a 1 degree resolution. So it's a 200 degree window. And so the question, of course, is how fast is it to transfer those profiles? And then because we're sending them down at a 1 degree resolution, but we need the 0.1 degree resolution, so we interpolate between those 1 degree samples. So here's a better picture of how that valve profile transfer happens. So here you've got the exhaust valve open profile, and then the exhaust valve closed profile, and then the intake valve open and intake valve closed. Now with this system, we can move the starting point, the start angle, on any one of those. So we can reposition it like a cam phaser, but we can also just send down a whole new profile as a cam switcher. So we can set up any profile we want and send it down in real time. So we looked at how long it takes. Well, I'll talk about that in a second. So what happens is the Simulink model gets an interrupt at a specific crank angle. And so when it hits that window, it says, okay, it's time to transfer the profile for the next engine cycle. And so this is the interrupt service routine in Simulink to do that. So the first thing we do is we set the start angle for that next profile generation. And then we transfer the profile. So this is our 200 element array of the entire valve profile. This is for the exhaust valve close. So then the next thing it does is tell the FPGA which profile this is. So 1 is the exhaust valve close. And then it basically sets a flag that says, okay, load that profile. And then on the FPGA side, when that flag comes in and says, I have a new profile to load, it sets that start angle. It also takes that entire array and it does an interpolation on it to convert it from the 1 degree samples to actually crank angle ticks, which are actually 0.09375 degrees. So it's slightly better than our 0.1 degree requirement. But that interpolation is done in here. It copies in the profile and then clears that flag and says, okay, I'm ready for the next profile. All of this happens in under 60 microseconds. So, it's less than 1 crank degree. So it's more than fast enough to get that transferred down. Hopefully I'm doing okay on time. So here's a look at the interpolation. So the green samples are what was sent down from Simulink. And then the red samples are after we do our interpolation and conversion from degrees to crank angle ticks. And you see that it resyncs every 3 degrees. So here at 42, they're lined up. And then again at 45, they're lined up. So it would resynchronize every crank tooth, so every 3 degrees. So here's an actual valve profile that's generated from the system. So this is just a scope capture of the valve profile. So you've got your exhaust profile and then your intake profile. And actually, I've got another sample, which is where we just move the start of the exhaust, move the start angles a little bit, just to show you a little bit difference in the valve profile generation. And we can send down any profile we want with this system. So, in the interest of time, I'm kind of going through this pretty quickly, but let me kind of summarize what we did. So we did the system analysis to prove that the hardware was really capable. We designed that valve profile transfer mechanism. We had to design the FPGA to control that valve position to the required 0.1 degree resolution. We did also add, I didn't really talk about, we added a watchdog and some other fail-safe conditions in case we lost crank sync or we got an overspeed. We would set the valves into a safe position to shut down. We also added a feature to reduce compression when first cranking, just to ease starting. So this was all built on a 1-cylinder test application and used to prove that we had control of the angles better than the 0.1 degree requirement. It was actually used to kind of test and optimize different valve profiles. And now we're looking at a 6-cylinder system. And of course, the one challenge is if we need a different valve profile for each cylinder, then that would require us sending down 6 profiles And we would use our DMA FIFO feature in order to do that, to really speed up that valve profile transfer. We also, as I mentioned, we recommended that they upgrade some of the hardware to meet some of these speed requirements. So that's going on as well. So just a little bit about LHP Panthera RCP Suite. We released our 2.0 version in August at NI Week. We now cover all of the National Instruments Linux RT targets, including the SOM, which if you're familiar with that, it's like the size of a deck of cards with the dual core micro and FPGA, really good for embedded ECU type applications. We also target all of the SB-RIOs that run on Linux, including the MyRIO or RoboRIO. So those could even be good for academic type applications. We added a bunch of IoT type support. We added Wi-Fi, Ethernet, Modbus and things. We also added the DMA FIFO features and embedded CAN support that we needed for the single board RIOs. And we're always expanding our Simulink library. This is a quick shot of some of the hardware that we developed that supports on all of this. So these are what we call our rapid prototyping unit family. We've got the small evaluation kit, which people can use to just, if they want to try out Panthera. It actually comes with some sensors and actuators, or you can hook up a couple of sensors and actuators to it and do some simple application. We have the engine control toolkit, which you can actually see in our booth, that is capable of running up to a 6-cylinder engine. And we can build the bigger systems to run larger engines with more I/O, of course.